Okay, good afternoon, everyone. Sorry for the delay. In today's lecture, I'm going to talk about path. Path is so important. And before we talk about path, we couldn't talk about other things like routing or dynamic traffic assignment. Today's outline consists of three things. The big O notation, which is a tool to analyze those time complexity or efficiency of the shortest path algorithms, and Dijkstra's shortest path algorithm. I think most of you may have already learned this algorithm like 3 or 4 times when you are learning some classes like optimization or data structure or traffic assignment. But I promise you, this lecture will be different. The third thing is about the shortest path problem in transportation. Okay? So, the first thing I want to talk about is the big O notation that we use to analyze the time complexity. It can be used to analyze the memory usage, but I'm only talking about time complexity here. So big O notation is a method used to evaluate or describe the worst or average performance of an algorithm. So let's say we have an algorithm, and this algorithm has a critical parameter called n, and with this n or problem size increasing, the total number of times we are going to execute the most time-consuming part is Fn. Let me say that again. So we have a function called Fn. This Fn describes how many times we are going to execute the most time-consuming code or most time-consuming statement in the program. And the fastest growing part will determine the order of this Fn, and it can be described by On. So for example, if n is a parameter of the problem, and if n is given, we can calculate the total number of times we are going to execute the most important part, the most time-consuming part. And Fn is equal to this thing. And out of these 4 elements, the fastest growing part is this part, n to the power of 3. Because when n is growing large, this part is the biggest. So this Fn can be summarized using the big notation. We can say big O and n cubed. So do you have any question about this? Now let me give you some example. The first one is called O1. It's constant time. This means no matter how big your problem is, the time we consumed, this algorithm consumed, is always constant. For example, in this program, this function has 2 inputs. The first one is an array of integers. The second one is the index. We want to get from this array a number with that index. Then this function, no matter how big your array is, no matter what your index is, it's taking the constant amount of time. So it's O1. But the next example will be On is linear time. For example, we want to calculate the summation of an array. And the amount of time will increase as the array size increases. Right? So you have you make a summation of 10 numbers, and this will take half the time than the case you want to do a summation for 20 numbers, right? So this is called linear time. The next example is called logarithmic time. So, and this is a figure showing you about binary search. What's binary search? Binary search here is an array, but it's already sorted. So for example, it's from small to big. And you want to find a number in this array. For example, this is 1 to 100, and you want to find where 33 is. And you know that these numbers are sorted, so these are smaller ones, these are bigger ones. But you don't know if this number exists or where it is. So you first look at the center point. Then you can decide if you want to search the left part or the right part. By doing this, you are doing a binary search. So if the size of this array is 2 to the power of n, then at most you have to search n times, right? And in this case, the time complexity is called logarithmic time. Do you have difficulty understand this? So if the length is 2 to the power of n, you have to search at most n times. And we mark this as O log n. Typically, we say log n to the base of something, but in this big O notation, we just omit this base. So we say big log n. The next case is called n squared. So if we want to calculate a multiplication table, n by n multiplication table, then how many calculations are we going to perform? It will be n squared. So 10 by 10, it will be 100 numbers to calculate. This is called O n squared. You may say that we only need to calculate half of them, because A multiplied by B is equal to B multiplied by A. That make it half of n squared. But we don't care about the constant. So half 0.5 n squared is equal to O n squared. Okay, so that's the time complexity. Are we all clear about these things? And the importance of this thing is when n grows very large, for example in the transportation program, let's compare the performances. If a function has time complexity of n1, it takes 1 millisecond. Then with log n, it takes 20 milliseconds. If it's O n, it will take you 17 minutes. But with n squared, it will take you 31.7 years. And that shows you if the problem size is very big, you may want to optimize your algorithm sometimes. Otherwise, it will take you 30 years to get the result. See that? So to warm up, I will have a quiz. So try to answer this very quickly, okay? So I'm going to give you a function. Tell me the time complexity of this function. A function A with input n is returning n cubed plus n squared plus n to the power of 5. What's the time complexity? Somebody answer me.
1.
1? Yes. Right. The answer is 1, because no matter how big n is, you only execute this function one time. I mean, this sentence is only executed one time. Okay? All clear? Now, we go to the next topic of today, which is Dijkstra's algorithm. This is the animation of Dijkstra's algorithm. Dijkstra, Esther Weber Dijkstra, is a Dutch computer scientist. He's not a transportation scientist nor a transportation engineer. And he was born in 1930 and he died in 2002. He was a professor at the University of Austin. University of Texas, Austin. And this animation give you a first impression of this algorithm. So this is starting point. By using Dijkstra's algorithm, we can create a shortest path tree originated from the starting point. So the result of Dijkstra's algorithm will be a shortest path tree from the start point. And I want to talk about the importance of this algorithm. If you ask me to rank the importance of algorithms in transportation, I would say this is the most important one. Without this algorithm, we will have to compare all possible paths from A to B and then find the shortest one. And this will be very, very time consuming. It has very big time complexity. And as a result, we will have no GPS. no traffic simulation, no travel demand forecasting, and we don't have current transportation science. So if you are required to remember only one algorithm in transportation, this will be the one. So if I am to predict in 100 years what the transportation science will be, I'm 100% sure that this algorithm will still be there. But user equilibrium or system optimal or any dynamic traffic assignment things, they may not be there. Okay, I rank this as the most important algorithm in transportation. Although the inventor of this algorithm is not a transportation engineer, this is the foundation of transportation. This algorithm has some assumptions which are very obvious, but I want to mention them first. So we formulate or we abstract we have an abstract network, and this network is represented by a bidirectional graph, which means A to B is different from B to A. Here A and B are nodes. And for each link, we have travel time or cost as its weight. This weight, if it's from the point A to the same point, it will be 0. And if it's from A to B, it will be positive or at least non-negative. That's very close to our to the reality, because we cannot travel on a link to save some time, right? So the travel time of any link is always positive. That's obvious, right? But what if the weight of A to B is negative? What will happen? That would mean if you travel along this link, then you are traveling along to the previous time. And you are a time traveler. That's impossible. And we assume that there is only one link